Welcome to lesson 13 of Stoechiometric Organometallics. Today we start with metal-specific features. Magnesium is in focus today, especially the so-called Magnesium-Ene reaction. So we will see what that is. First of all, you certainly remember the general scheme of a Diels-Alder reaction. We have a diene and an olefin, and it reacts in a concerted process to form a cyclohexene. Let's modify the diene component, simply such a propene system. And now imagine a concerted process. Well, okay, let us explain it this way. An aromatic transition state, in this case, involving 6 pi electrons. So here we can also imagine a process where 6 electrons take part. 2 of these electrons are sigma electrons. It could give this result. And this type of reaction indeed works. And it's called the Ene reaction. So, let's have a look for examples. A thermal induced transformation occurs. Well, just as in the general scheme, a CC bond is formed, while those 2 CC double bonds are transformed in single bonds. 1 hydrogen is transferred, and here a double bond is formed. It's the same here in this case. This hydrogen is transferred to this position. The CC bond is formed between this and that position, and here the double bond is formed. So this is a nice example of the Ene reaction. And what we learn is that as this is a concerted process, the groups are transferred from the same side to the same side of the olefin. Yeah, so that means that we will have a cis product in the end. Well, selectively, unfortunately in this case we need a rather high temperature, 450 degrees. There are examples where we have a lower temperature. This one, for instance. this is the allylic system. Most interestingly, this maleic anhydride is also known as a very good dienophile and yields aldo reactions. And indeed, also the ene reaction works very well in xylene at reflux. So approximately 140 degrees. Resulting in this product. By the way, you might notice that this starting allylic component is a terpenoid, a natural product, and this is beta-pinene. Well, let's modify this general scheme a bit more. We stay with a system like that, this propene system. But here, we change from one CH2 group to an oxygen. So, reaction is such a system with a carbonyl group. Does this transformation work? Yes, it works very well, especially if we activate the carbonyl group by a Lewis acid. Might also be a chiral Lewis acid, and we could introduce some chiral centers then. Stereoselectively, when we have some additional substituents here. This type of reaction is also some kind of ene reaction, a carbonyl-ene reaction. Well, again, let's introduce a small change here. Put in a magnesium halide instead of that hydrogen. So, we could call that a carbonyl Magnesium-Ene reaction, but while this name is not usually applied, we know that this is an addition reaction to a carbonyl group with an organomagnesium, and this is a typical Grignard reaction, while a bit atypical, because also this reaction proceeds through a 6-membered transition state. So, well, if you have an allyl magnesium compound, then there is an equilibrium between those allylic structures, and the equilibrium is by far on the side of the less sterically hindered allyl magnesium compound. So that means even if you start with this bromobutene, you would have this as the main component in the reaction. For instance, with formaldehyde, the Lewis acidic magnesium coordinates to the oxygen, and then, well, this is the start for the formation of the six-membered transition state. And as you will notice, this is indeed a bit funny, although this is the main structure of the organomagnesium compound in the equilibrium. The final product, this alcohol, looks like it derives from a 1,2 reaction of this starting allyl magnesium compound. So finally, let's change the general scheme back from the carbonyl just to an olefin. Sorry. And there is something wrong. That's the reason why it doesn't work. So, yes. Now it's correct. Okay. So, this reaction, an Ene reaction where we have changed one hydrogen to a magnesium halide, and this is then called the Magnesium-Ene reaction as the general scheme. And of course this works, otherwise I wouldn't have done this introduction. So, first example of an intermolecular magnesium-Ene reaction with an especially reactive olefin, since it's a strained olefin. So, in diethyl ether, temperatures between 0 and 20 degrees, the Ene reaction will occur. And again, a Syn addition reaction Well, essentially then it is also a carbomagnetization, but with a special mechanism, this concerted mechanism with a 6-membered transition state. And well, you might trap that with an electrophile and you will figure out that this step proceeds with about 85% yield. For the intramolecular, Magnesium-Ene reaction, there are 3 types. Type 1, a ring closure reaction occurs and all olefinic parts are oriented exocyclic. This is type 2. One olefin is oriented endocyclic in the ring. Well, and type 3, finally, then all olefinic parts are oriented endocyclic. Resulting in structures like that. So, the following we will see some examples and additional remark. As you notice, the more electron-rich the system, very often the lower the temperature that is necessary to activate. We know that from other examples. Well, you might know the Cope rearrangement. This Cope rearrangement needs, well, about 180 degrees. And such potassium alcoholates, or also lithium alcoholates, they also undergo that Cope rearrangement. finally leading to these structures, delta epsilon unsaturated carbonyl compounds. And since this is a more electron-rich system, this also in electronic contact, of course, with the six-membered aromatic transition state, the reaction proceeds at much more moderate reaction conditions. About 50 to 70 degrees are sufficient for the so-called oxy-cope rearrangement. But back to the magnesium-Ene reaction. Some examples. So, what would be the result of that? Here, the six-membered transition state, ring closure reaction from this carbon to that one. I think it's very easy to understand. Introducing such a reaction step as the key step in a natural product synthesis. And most of these natural product syntheses have been performed by the group of Oppolzer, I think in Switzerland, hope that's right. So, here by the key step, the magnesium-Ene reaction as key step, the carbon skeleton of, well, it's called skytanthene, was synthesized. Already at minus 40 degrees, 16 hours reaction time, the magnesium-Ene reaction occurs for this system. It's stereoselectively a Syn addition process. And an oxidation, well, it's claimed to be done just with oxygen, introduces the alcohol. So, next step. An alcohol functionality is introduced here. Should be clear for everyone from organic chemistry 2 that this is, of course, the addition of water in an anti-Markovnikov sense to an olefin, and well, best method for that is the hydroboration and oxidative workup. So, EH3, and then secondly, sodium hydroxide, basic conditions with hydrogen peroxide. So, for getting to the target compound, it's an alkaloid, we have to introduce the nitrogen functionality. Well, it's clear that we need methylamine as the nucleophile. So, secondly, that nucleophile, and first of all, we have to transfer these OH group into good leaving groups. And this has been done with paratoluene sulfonic acid chloride, and we need a base pyridine in that case. That's the whole synthesis to this natural product. Another synthesis to a terpenoid called capnylene. And here we learn how to introduce that allylic magnesium halide. Very straightforward. If you treat this aldehyde first with vinyl lithium, well, I should write down what you get then. You get this allylic alcohol. Secondly, treating that with thionyl chloride. Well, exchanges the OH group against a chloride, and at the same time rearranging this system. And here we have now the allylic chloride. So this two-step transformation was successfully done with 76% yield. Activated magnesium will form the Grignard reagent. Now we have that nicely set up for the Magnesium-Ene reaction. So an addition process as usual. So, and now acrolein is added. Giving again an allylic alcohol the yield achieved was 57%. So what might be the problem here? Why is it only 57%? Okay, you always have some problems with that formation of allylic magnesium halides if it's not activated enough. We have discussed that problem with allylic radicals as intermediates before. But the other problem is this step, certainly, because you have here 1,2 reaction while competing with the conjugated addition reaction, the 1,4 addition reaction. Well, we will learn tomorrow that we can solve that problem with a transmetallation. We should change to organocerium to get a nice yield for the 1,2 addition process. But we will discuss that in detail tomorrow. So again, we have an allylic alcohol system, and while in the neighborhood this olefin, that process, the transformation to an allylic chloride, and then forming the Grignard reagent again, is repeated. (72% for that step. And well, of course, Magnesium-Ene as cyclization process. So should be the type 1 Magnesium-Ene cyclization. Okay. Oxidation was the next step. For alcohol functionality, then a short sequence where we don't need the details. Having an aldehyde here, and a ketone there, well, clearly this has been oxidized, then maybe a Grignard addition reaction oxidizing again, that we have that methyl ketone on that side. On the other side, the olefin transforming to the aldehyde. This is, of course, done with an ozonolysis. So, and now, treating this compound with the base aldol condensation reaction. Another 5-membered ring is formed. So let's write down our target compound, the capnylene here. An exocyclic double bond. So, well, we could just guess what will be the methods of choice for getting from here to there. 2 steps. Well, first step is to reduce that double bond, hydrogenation under the appropriate reaction conditions, and then we have a carbonyl group to transform that to the exocyclic double bond. This is simply a Wittig reaction. So, one last natural product synthesis from Oppolzer's group. Once again, a strange name, sinularine. Structure of the target compound is this. So, once again, the key step at this Organometallics system is the intramolecular Magnesium-Ene reaction. What I found interesting is that Oppolzer introduces a catalyst for the formation of the Grignard reagent, and the catalyst is 2 mol% of something we already know, that magnesium antrazine complex, 2 mol% are enough to catalyze the formation of the Grignard reagent. So, this reaction was performed at low temperature, -78 degrees, and the Magnesium-Ene reaction occurs while warming up, and it's a Syn addition process. Well, the carbon skeleton is almost set up. We need a 1 carbon component, maybe simply formaldehyde here. On the other hand, an isomerization from the endo position to the exo position of finally the isopropyl group has to be achieved. Okay, that needs a couple of more steps, but I think the principle is clear. Another subject for today is, well, when you are preparing organolithium or organomagnesium compounds, or these bases like LDA, you very often need to know about the quality and the concentration and the quality of your organometallic reagent. Also, of course, if you just normally buy your butyllithium, it is a 1.6 molar solution in hexane, and others in the group might have already used it, and maybe we were not that careful in avoiding moisture and hydrolysis. And sooner or later you will be in need of testing the quality of your organometallic reagent. And this is normally done by titration. You will find a lot of procedures to do that, a lot of indicators, and let's have a look on some of those indicators. So, subject is titrating Grignard reagents are organolithium compounds and well, also strong bases like LDA. One nice indicator which works for all of those Grignard reagents, organolithium compounds, and LDA is this one. Well, you can easily synthesize this because it's simply the phenyl hydrazone of salicylic aldehyde. That's it. If you deprotonate this with a strong base, you of course deprotonate at the most acidic position, and this is the phenolic hydrogen. If you do so in a titration, that means you have a certain concentration of that compound, and you add either Grignard reagent, organolithium, or LDA, then it will be deprotonated. So, one equivalent of the strong base, R, MgX, and so on. Please keep in mind that Grignard reagents are generally far less basic than organolithium compounds. However, Grignard reagents are basic enough to deprotonate here, and they also are basic enough to deprotonate a second time with hydrogen. Yeah? So, first of all, the solution turns yellow, and it keeps the yellow color, which becomes a bit deeper and deeper, until you have added a full one equivalent of the stuff you want to test. So, one drop more of your strong base will start to produce the dianion. And this has another color, it turns red. So, having a 1 molar solution of that and titrating it, or another, you have to know the molarity of your solution, and finding out what is one equivalent. You can do that by this operation, first drop, and you have that a turning point. Yeah. Okay, it's not that nice a change from yellow to red. Would be better if you would have a change from colorless to something. Yeah. We will see indicators that do that job in the following. However, these indicators doesn't work with organomagnesium compounds. You need stronger bases to deprotonate those for a second time to form the dianion. So, second example. As I said, this doesn't work with organomagnesium, but with LDA and with organolithium. So let's say one equivalent of organolithium so, and this time the hydrozone hydrogen is the most acidic one. Well, okay, of course, activated by the tosyl group. And again, one drop more. Then from the colorless monoanion, we get to the bis anion, dianion, so here as lithium compound, and which is yellow at low concentration, red at higher concentrations. So as soon as it turned red, you have for sure over-titrated the system. Two more similar, very similar examples. Pivaluyl amides. Most acidic position is the amide proton. First, deprotonation with one equivalent. Still colorless. With R prime either a hydrogen or a phenyl group. One drop more of a strong base than deprotonates in benzoylic position, or if it's a phenyl group, double benzoylic position. And this one is yellow in the case of R prime a hydrogen, or yellow to orange with phenyl. Very similar the next one, but a bit newly introduced also. By the way, the advantage of this system is that it is less hygroscopic than other indicators. And you might imagine it's not good to introduce a wet indicator in this titration process. So, also a rather non-hygroscopic one is this one. It works very similar to the one before. First deprotonation and one drop more. So here again, one equivalent, one drop more. The dianion is formed of a bismetallated one, again in the benzoylic position. And here, the change in color is from colorless to a nice blue, which is, of course, easily noticed. Same principle, although are not very much related, unless the fact that you could also deprotonate this diphenyl acetic acid twice. So, first deprotonation forms the simple lithium carboxylate, and the second one the corresponding enolate. Change in color from colorless to yellow. An interesting case is this one. Triphenyl methane. Deprotonating triphenyl methane gives somewhat pink color. But how can you titrate that? Having a triphenyl methane solution and adding butyllithium, strong base, well, will give immediately the pink color. So the trick is you need a system which you can deprotonate twice. And with the second deprotonation, you get the formation of that color. So, very simple. Just put in another component which doesn't give a color but is easily deprotonated. An alcohol. So, and this is done, a 1 molar solution of an alcohol and a little bit of such an indicator. That's it. Essentially, it's the same as that we have seen before. But there we have that those two acidic positions in one molecule. So, this isobutanol is one alcohol which is often used. And the other one that is used, well, nowadays I think even more often, because it's less hydrophilic. This is menthol. So, with the first deprotonation, you form the lithium alcoholate and still have that indicator untouched. 1 drop more, you still have lithium alcoholate, but you start to form the indicator. And you will get, therefore, a response, a color response of the system. The combination of an alcohol and an indicator is also often done with either phenanthroline or with two prime dipyridine or dipyridyl. This one. Same process, same principle as before. By the way, you can titrate several times in the same solution. You have a turning point. Well, maybe add a little bit of alcohol for neutralize it, and then simply start again. So, and the color change here in this, for this type, is described in Wikipedia as that. That the lithium is chelated by the bipyridine system, and it should be essentially the same with the phenanthroline system, and it's claimed that this has a deep red color, indicating the turning point. While I'm very much in doubt that this is correct, since there is the so-called Ireland titration, which is specific for amide bases in presence of alcoholates and hydroxides. And for the Ireland titration, the indicator is formed. So, with N-butylithium undergoes an addition reaction to this bipyrydyl system and certainly also to the phenanthroline system. And this has, as described by Ireland, a blue or a red to blue color. Remember what's written here. Hydrolysis gives a colorless indicator. And this indicator then is specifically deprotonated by amide bases in the presence of hydroxide and alcoholates, as I said before. The structure was proven because oxidizing it, molecular oxygen, then it aromatizes oxidatively to give this one. So I'm pretty sure that also in that case for that titration with the alcohol and the bluish color, red bluish color derives from that and not from that complex. So this is an overview about the methods for single titration. These methods have a disadvantage. They tell you something, well, somewhat reliable about the concentration of your butylithium or organomagnesium solution, but it doesn't tell you anything about the quality. Well, remember, you start, when you buy it, with a 1.6 molar solution of butylithium. After a while, several people have used it, a bit is hydrolyzed. Maybe more than 50% might be hydrolyzed. And well, then white precipitate is formed within your flask, the bottle, and this derives from lithium hydroxide. Nevertheless, there is a solubility of lithium hydroxide in butylithium hexane solution. there might be, well, 10% of lithium hydroxide in that solution, and this is bad quality, while 3% lithium hydroxide is, well, normal to good quality. So that means you might have in solution residual base, that lithium hydroxide. How can you determine that? It might be necessary or a good idea to determine. And this is done by the so-called Gilman double titration. First titration, very simple. You take, well, about 1 milliliter of your solution and hydrolyze it. Completely hydrolyze it, and then you titrate that against, for instance, phenolphthalein as indicator with 1 molar hydrochloride solution. By titrating this, you get the total base content of the probe you test. So, total base, have a simple titration. Secondly, you treat that butyllithium with an excess of 1,2-dibromoethane. What will happen? Monolithiation, forming butyl bromide. And this monolithiated species, which of course eliminates lithium bromide, forming ethane. So you have destroyed the butyllithium without forming any base. So you extract that with water, then having all the lithium hydroxide, all that residual base, then of course in the water solution you titrate again, and that's the way to figure out the amount of residual base. You should do that 3 times. It makes overall 6 titration that you have a reliable result. This explains why these single titration methods are preferred. Although also those methods you should do 3 times for getting reliable results. Yeah? So with the old Gilman titration, you get additional information about the quality of your organometallic reagent. Yeah? I think this is important to keep in mind. Finish for today. Tomorrow we go on with metal-specific features, and tomorrow will be about organocerium chemistry. Thank you for listening. See you tomorrow.